Welcome to Math with Professor V. In this video, I'll be solving the latest exam that I gave to my Calculus 2 class, and it's all on sequences and series. I'm going to be explaining a little bit as I work through the problems, but if you need a full depth lecture or explanation on any of the topics covered, then head to the description box. I have all of the video lectures linked that pertain to this unit down below. But let's just jump into it. I know so many students get scared when they hear they're going to learn sequences and series. I think it's overly hyped as just this super confusing topic. It's not. You just need someone who can talk to you in everyday language and break it down in a way that's understandable. So that's what I'm here to do. All right. First thing, we're going to talk about our sequences before we get into series. And usually you don't talk about them for too long in calc, so that's why students kind of forget some stuff. The first question says, find the limit of the sequence if it converges, otherwise indicate divergence. So when you're asked to figure out if a sequence, not a series, a sequence converges, all you need to do is take the limit as n goes to infinity of an. And if you get L, which is some finite number, then it converges and you're done. This is a lot easier than testing if a series converges or not, because remember, in a sequence you just have an ordered list of terms. You're not actually adding them up. So we say it converges just so long as the terms are heading or approaching some finite number. Okay, so here we go. Let me look at this first one. I have the limit. I'm going to take the limit as n goes to infinity of an, which is natural log 5n minus 5 minus natural log 4n minus 7. Okay, right off the bat, do you remember graph of natural log of x? Yes, I hope so. I hope so. If not, let me help you remember. Here's y, here's x. It goes through 1, 0, and rough sketch looks something like this. We've got a little vertical asymptote situation going on. Okay, so as the argument here gets very, very large, you can see natural log is going to go to infinity, and this will also approach infinity, and we're in a wee bit of trouble because there's a minus sign here, so we have infinity minus infinity. That's an indeterminate form. They don't cancel out, remember? So what do? Well, thank goodness we're given natural logs. I can combine them into a single logarithm. So I'm going to write this as the limit. N approaches infinity, natural log 5n minus 5 over 4n minus 7. Okay, what does that let me do? Well, now I have numerator, denominator both going to infinity. I don't want to use L'Hopital's rule because remember, you can only use L'Hopital's rule on differentiable functions, and a sequence is definitely not differentiable, but we don't need L'Hopital's rule. I can just go through, divide everybody here in the argument by the highest power of n from the denominator. So I'm going to divide everybody by n to the first. So let's hop to it. And then now I have limit n goes to infinity. You can just keep the natural log hanging out there. Minus 5 over n over 4 minus 7 over n. And then there we go. This 5 over n goes to 0, 7 over n goes to 0, and all I'm left with now is natural log of 5/4. Since this is a finite number, the limit exists, and I can say that the sequence is convergent. Bada bing, bada boom. Done. It doesn't matter what number it converges to. It could even be 1,000,000. When we're talking about a sequence, just so long as the limit exists and it's finite, you're good. Okay, the next one's a little spicier. A sub n equals n times sine of 1 over n. So let's see what's going on here. We have the limit n goes to infinity of n times sine of 1 over n. All right, so as n gets large, this first term's going to infinity. Where's 1 over n going if n goes to infinity? It goes to 0, right? And sine of 0, that'll be approaching 0. Oh no, we have another indeterminate form. Infinity times 0. It's not 0, guys, no. if you're rusty on the indeterminate forms, let me link some videos for you up here, okay? I'll put some more in the description. I've got quite the collection. Okay, so what should we do? Well, the trick is I want to see if I can get again to the form 0 over 0 or infinity over infinity. That usually lets me use L'Hopital's rule or something else. So here I'm going to flip that n in the bottom. So I'm going to write this as the limit n goes to infinity, sine of 1 over n, over, and then if I move this n to the denominator, it becomes 1 over n, right? Dividing by 1 over n is the same as multiplying by n. And then now, if you need to, and some students did do this while I was grading their test, they redefined everything as a function of x so that they could go ahead and use L'Hopital's rule. You don't have to do all that though. If you remember, okay, if you recall that the limit as theta approaches 0 of sine theta over theta equals 1. That's from Calc 1. So hopefully you remember. If not, then you can do L'Hopital's rule, just a few more steps. And as n goes to infinity, you might be saying, I don't have that though. But we do really. As n is going to infinity, 1 over n is going to 0. So we do have a limit of this form. If you want to rewrite things really crystal clear, you could say, let's let t equal 1 over n. Then, as n approaches infinity, 1 over n approaches 0, which is where t is going to go, okay? So then I could rewrite this as the limit as t approaches 0 of sine of t over t, which equals 1. And what do I care about this limit? That it's a finite number. So then I could say this means an, which is n times sine 1 over n, converges. And that's it. Okay, one more. This time we have a sub n equals 1 plus 5 over n raised to the n. So again, let's take the limit as n goes to infinity of a sub n. So this is 1 plus 5 over n to the n. Now 5 over n, this term right here is going to go to 0. So this whole base is approaching 1. And then this exponent is approaching infinity. So guess what? Yet another indeterminate form, 1 to the infinity. Do you know how many indeterminate forms there are total? Very good. There's 7. Yes. I would say there's 7 indeterminate forms, like 7 deadly sins. Then you'll remember. 3 indeterminate powers. So 1 to the infinity, 0 to the 0, and then I'll let you research what the third indeterminate power is. So how do we deal with these? We have to use L'Hopital's rule, okay? And we want to move the exponent to the front in order to do L'Hopital's rule. So I'm going to introduce natural log, okay? You should have seen this kind of indeterminate form when you were in Calc 1, when you were learning L'Hopital's rule, hopefully. Now, obviously, we can only use L'Hopital's rule on differentiable functions, so I need to redefine this to be a function of x. So I'm going to say, all right, let's let f of x be 1 plus 5 over x to the x, all right? Then natural log of f of x is natural log of 1 plus 5 over x raised to the x. Remind yourself, what am I doing this natural log business for? So I could move that x to the front, okay? So we're going to write this as x times natural log 1 plus 5 over x. And then the whole point, remember, if we're going to use L'Hopital's rule, we have to have indeterminate form of the type 0 over 0 or infinity over infinity, meaning we need to make this thing a fraction somehow. So never move the natural log. Write that down. Never move the natural log, move the other term to be in the denominator. So we've got natural log 1 plus 5 over x over 1 over x. Great. So now I'm going to take the limit as x goes to infinity of natural log of f of x. So natural log of 1 plus 5 over x over 1 over x. Now I need to verify that I have the correct indeterminate form type before I go ahead and do L'Hopital's rule. So you have to check that you have either this case or this case, all right? If you do L'Hopital's rule when you don't have one of those two types, it will not work out for you. So it's not a pointless exercise to check. All right, let's see. So x is going to infinity, 5 over x, we know that's going to 0. So the numerator is going to natural log of 1, that's 0. And then 1 over x, yeah, that's going to 0. So indeed, I have 0 over 0. Great. Then let's go do L'Hopital's rule with a clean conscience. It was warranted. Limit x goes to infinity. Now, when you do L'Hopital's rule, I always say it's like the illegal quotient rule. Like, you're not doing the quotient rule. You're just taking derivative of the numerator and then derivative of denominator separately. So derivative of natural log something is always 1 over the something, 1 plus 5 over x, times, I have to do the chain rule and multiply by the derivative of what's inside, yes? Okay, so what's the derivative of 1 plus 5 over x? Derivative of 1 is 0. If you want to remind yourself, 5 over x is 5x to the negative first. So its derivative would be negative 5x to the negative second or over x squared. Okay, that's the derivative of the top. Derivative of the bottom, 1 over x is x to the negative first. So its derivative would be negative 1 x to the negative second or negative 1 over x squared. Beautiful, beautiful. Now let's clean up. Let's see where we're at. Oh, this is exciting because notice these two negatives will cancel. I'm also dividing by x squared in the top, dividing by x squared in the bottom, so that cancels out. So now I'm just going to write this here as limit x goes to infinity. I have 5 over 1 plus 5 over x. Wow, 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 so beautiful. So then as x goes to infinity, 5 over x goes to 0. I'm just going to be left with 5 over 1, which is 5. Now, hold on, we're not done. What is 5? 5 was the limit as x approached infinity of natural log of f of x. So let's summarize that so we can answer the question. So this means the limit as x approaches infinity of the natural log of f of x was equal to 5. But we added that natural log, right? That was not there in the original problem. So how do I get rid of it? Well, I can just say e raised to both sides and then clean that up. So this means the limit, you can interchange and pass the limit e through the limit. Limit as x goes to infinity of e to the natural log of f of x equals e to the 5th. So then basically we know by our properties, those will cancel out. And then we have the limit as x goes to infinity of f of x equals e to the 5th. And remember, f of x I put in as a replacement for the sequence. That way I could use L'Hopital's rule. So this tells us, in grand summary, the limit as n goes to infinity of an, which was 1 plus 5 over n to the n, is e to the 5th. Okay, now I've told my students a bunch of times, they don't have to show me this whole process. So check with your instructor. I'm cool with them just getting 5 and then summarizing, rewriting the original sequence and remembering to take e raised to whatever they got here. So just ask your professor if they're okay with that too. If they're not though, it's, this should make sense to you. That's the why we do it. It's just so repetitive. I don't need to see it all the time. Okay. All right. So if you're in my class, don't be paranoid. If you stopped here and then you just went here, you got full credit. Okay. Good. Good, good. Another sequence problem. Determine if the sequence is monotonic and if it is bounded. Ooh. Okay. So monotonic means that the sequence is always increasing or always decreasing. There's a few ways to check. One of the ways to check is you compare an plus 1 versus an. You compare the term that follows with the term prior, and if you can show that one is always bigger than the other, then you know the sequence is either always increasing or decreasing. So I usually try that first because it's like the least invasive method. So an plus 1 would be 5 times n plus 1 plus 1 over n plus 1 plus 1, and this is 5n plus 6 over n plus 2. It's not obvious whether or not that's bigger or smaller than 5n plus 1 over n plus 1. Why do I say that? Well, this denominator got bigger, which means this whole thing is smaller when there's a bigger denominator, but then also the numerator got bigger at the same time. So it's not obvious. What do you do when it's not obvious? You go, oh, I'm just going to take a derivative and see if I could figure out based on the sign of the derivative if there's ever going to be a change in increasing, decreasing. But can we take the derivative of a sequence? Are they differentiable? No. So we just have to redefine it as a function. So we're going to let f of x equal 5x plus 1 over x plus 1. And then let's take the derivative. Now we're doing OG quotient rule. I sing the little song, high over low. Think the numerator is high, denominator is low. The song goes, low-de high minus high-de low over low-low. It's more like a rap, okay? So low is the denominator, d high is 5, minus high, the numerator, d low, derivative of the bottom is 1, over low-low. You could also say square the bottom, away you go. That's the remix. Okay, what does this give me? 5x plus 5 minus 5x minus 1 over x plus 1 squared. And then the 5x's cancel. I'm just left with now a 4 in the numerator, right? Over x plus 1 squared. Well, the denominator is squared. In the numerator, I've got a positive constant, so this derivative is always positive. If the derivative is positive, that means f is an increasing function, which means my sequence an is monotonic increasing. Wow. Now, that's settled. The other thing the problem asked is if the sequence is bounded. Bounded meaning I can find a lower bound on all of the terms of the sequence and an upper bound on all of the terms of the sequence. So let's think. The sequence is increasing, monotonic. So that means A1, the first term, is going to be my lower bound. Okay, so lower bound, let's find A1. What would it be? Let me plug in 1 for n. 5 plus 1 over 1 plus 1. This is 6 over 2, so 3. There's my lower bound. Now, what I need to check is, do the terms go up, 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 up indefinitely without bound, or do they level off? Is there an upper bound also? So if there's like an upper bound, it means they increase, but they stay below that upper bound. How would you check where the terms go long term? You take a limit to infinity. That's exactly what you do. So we're going to look at the limit as n goes to infinity of 5n plus 1 over n plus 1. So usually once you've verified that your sequence is monotonic, the first term will either be your upper bound or lower bound, depending on if it's increasing or decreasing. And then to see if you have the other bound, you take the limit to infinity. That's the typical protocol. So no, we're not doing L'Hopital's rule. This is a sequence, right? So we're just going to divide by n. And then we have here the limit as n approaches infinity. The numerator is going to be 5 plus 1 over n, and then 1 plus 1 over n downstairs. This term goes to 0. This term goes to 0. So I just have 5 as my limit. So that means the terms approach 5, not infinity. They don't keep going up, up, up without bound. So that's my upper bound. Upper bound, 5. So we could say yes, AN is monotonic and bounded. And this is actually very special because these two conditions tell me that AN is also a convergent sequence. But I didn't ask that in the question. I had a few stellar little students who wanted to throw that in and tell me that they knew that, and I was so impressed. They wow me all the time. But yes, those are two conditions that guarantee that a sequence will be convergent as well. If you decide to become a math major, then you're going to study that more. Yes, you will. Okay, how was that? Next problem deals with finding sums of series. Now, most of the time when dealing with infinite series, all you do is say whether or not they're convergent or divergent. It's very rare that we can find their sum. And when you're asked to find their sum, it's a big clue as to what kind of approach you need to take. Because the only kinds of series whose sum we can find are either geometric, telescoping, or certain Maclaurin series. So the minute you see in the direction someone telling you to find the sum, you go, it's gotta be one of these three. It's not a Maclaurin series. It's not telescoping. I don't see that happening, but I certainly see how this is geometric. So in order to find the sum, remember we have the formula S. Sometimes it's S or you see S infinity. A over 1 minus R. A is the first term of the series. So that could either start at 0 or 1. You have to check, this one's starting at 1. But if it started at 0, then this would be based on plugging in 0. You got it? Okay. I have to identify R. And right now the way this is written is just a hot mess. So let's rewrite it and clean up, because I can't tell what R is. Look at this craziness. So AN is negative 1 to the n minus 1 times 2 over 9 to the n. I'm going to write this as negative 1 to the n, negative 1 to the negative first times 2 over 9 to the n. What you want to do is group everything together that's being raised to the n. So this is going to be negative 1/9 to the n. And then this other stuff here, this is just negative 1 to the negative first is still negative 1 times 2. So that's negative 2 outside. Isn't that much more clear? That's R. That's R. So can I find the sum of this series? Yes, because absolute value of R is 1/9, which is less than 1. And what's my first term? So if I plug in n equals 1, you could plug it in to either the original hot mess or this. You will get the same result as long as you didn't do anything illegal. So negative 1/9 raised to the first is negative 1/9 times 2 is positive 2/9. Okay, so the sum is going to be 2/9 over 1 minus, and some students did mess this up. It made me sad. R is negative 1/9. Negative 1/9. Okay. You don't put the absolute value in the summation formula. It will change the value of the sum of the series. You just check that absolute value of R is less than 1, but you have to use the original value of R here when finding the sum. So this is 2/9 over 1 plus 1/9. What is that? 10/9. So that's 2/10, aka 1/5. All right, beautiful, beautiful. Next, again, find the sum of the series. This is, again, going to deal with the fact that these terms belong to geometric series, okay? But you have to be careful. Caution. The sum of AN plus or minus BN only is equal to the sum of AN plus or minus the sum of BN if we know that the sum of an and the sum of bn are already convergent. So why am I saying that? Basically, you're not allowed to distribute this summation until you first confirm that both of the series for these terms independently are convergent. Okay, otherwise this is an illegal step. The math police will come snatch you quick, fast, and in a hurry. Okay, so you're just gonna say, you're gonna be a very careful math student, and you're gonna say consider. Consider the sum n equals 1 to infinity of 1 over 2n. That's the same as 1/2 to the n. Okay, 1 to the n is 1, so I can just swoosh it in the parentheses like that. So r is 1/2, and absolute value of r is less than 1. This is geometric, it converges. The sum, I'll say sum 1, because this is the first series I'm going to look at, is going to be the first term. Where is this starting? At 1. So if I plug in 1, that's going to be a 1/2 over 1 minus r, which was also a half. So I have a half over a half, which is 1. Okay, save that on the back burner. Now let's tackle the second little series. We have the sum n equals 1 to infinity. I'm just going to leave it as 1 over 9 to the n. Remember, that's the same as 1/9 to the n. R is 1/9. Absolute value of r is less than 1. Same reason, geometric convergent. So sum 2 is going to be the first term, which is 1/9, over 1 minus 1/9. So that's 1/9 over 8/9, which is 1/8. Since both were convergent, then I can go ahead and say this means the sum n equals 1 to infinity 1 over 2 to the n minus 1 over 9 to the n is equal to the sum n equals 1 to infinity 1 over 2 to the n minus the sum n equals 1 to infinity 1 over 9 to the n, which is 1 minus 1/8, which is 7/8. Okay? And this is very important later on. And if you study more advanced courses where you look at infinite series, you'll see that breaking up the terms can lead to huge problems when they're not independently convergent like that. Okay? Good. Let's look at another problem. Determine if the series converges or diverges. If the series converges, find its sum. There's that phrase again that I told you was super rare. If they tell you find the sum, it means this series is one of 3 kinds. It's either geometric, telescoping, or Maclaurin. It's certainly not geometric. I don't see anything being raised to the n. It does not look like a Maclaurin series to me. It is telescoping. Oh yes. So how do we deal with telescoping sums? We find S sub n, an expression for the nth partial sum, and then we take the limit as n goes to infinity of that expression, of S sub n. Okay, so how do we find S sub n? It's the sum. We have to change our index of summation. Usually we use I. I equals 1 to n. Why do we do that? Because this is not an infinite sum. We're summing up the first n terms, so you stop at n. And then you replace n with I in the expression for the term. So we have 1 over rad I plus 1 minus 1 over rad I plus 3. Good? Excellent. Now, for telescoping, you just start listing out the first few terms and the last few terms until you see a pattern, okay? So I'm going to start substituting in. Let's do I equals 1. I'm going to have 1 over rad 2 minus 1 over rad 4. And I know that simplifies, but it's not going to help me, so I just leave it. Do less. Plus, now let's move on to the next term. 1 over rad 2 plus 1 is 3 minus 1 over rad 5. Let's Let's move on. I equals 3, 1 over rad 4 minus 1 over rad 6. I equals 4. Now I have 1 over rad 5 minus 1 over 4 plus 3, 7, rad 7. Okay, plus dot, dot, dot. I feel good with this many, and I'm going to give you a life-changing tip. Are you ready for it? Yes. Look at the terms down here. How far apart are they? I plus 1, I plus 3. That's 2 apart, right? That means I should have 2 terms from the beginning that don't cancel out, that survive, and also 2 terms at the end. So look, I already see the lovely cancellation. Like here's positive 1 over rad 4, negative 1 over rad 4. Positive 1 over rad 5, negative 1 over rad 5. I didn't go far enough, but eventually this 1 over rad 6 and 1 over rad 7 will cancel. Who will not cancel out? Who will survive? 1 over rad 2 and 1 over rad 3. And I know that I will have 2 terms that don't cancel because these denominators are 2 apart. That's how you kind of get a feel that you're headed in the right direction, okay? Then at the end, you should also have 2 that don't cancel out. It should be matchy-matchy most of the time. I like to just start at the very end. So I'm going to do I equals n last. So then this would be 1 over rad n plus 1 minus 1 over rad n plus 3. Okay, and then who comes before n? Why n minus 1? So this would be 1 over rad n minus 1 plus 1 would just be rad n, yes? Minus 1 over n minus 1 plus 3n plus 2. I equals n minus 2. 1 over rad, now this will be n minus 1, won't it? Minus 1 over rad n plus 1. You can keep going if you're a particularly nervous person. I feel great, but you know, if you just want to make sure you don't mess up on the test. As soon as I notice, okay, this is going to cancel. And yeah, nothing will cancel with this guy, nor will anything cancel with this last one. But had I kept going, then, you know, this would have canceled later, the 1 over rad n, this would have canceled. But there's my 2 survivors from the front and my 2 survivors from the back. So I'm like, I'm good. I got everything I needed. So this is the nth partial sum. 1 over rad 2 plus 1 over rad 3 minus 1 over rad n plus 2 minus 1 over rad n plus 3. Now, what do we do with this? Well, we take the limit as n goes to infinity of s sub n, and we see where the terms go. So that would be the limit as n goes to infinity, 1 over rad 2 plus 1 over rad 3. I'm like so tempted to just do a copy paste because I'm on the iPad, but you know, if you're copying this down at home, let me not beat you to the punch. So let's be on the same page, rad n plus 3. Okay, the first 2 terms are constant. The last 2 go to 0, which tells me that the partial sums approach a finite number, 1 over rad 2 plus 1 over rad 3. So since that's finite, that means the series converges. And we could say the sum, n equals 1 to infinity, it was 1 over rad n plus 1 minus 1 over rad n plus 3 equals, yeah, isn't that cool? 1 over rad 2 plus 1 over rad 3. Obviously it converges. You can write that though if you want. I think the direction said if it converges, find its sum. So since we found the sum, we're good. Equals s. Now I feel really good. Okay, perfect. How was that? Fun? Do you like telescoping series? They would make me nervous because I never knew like if I listed everything out correctly. But then once I noticed that pattern, it really helped me be more confident. Okay, so these are 2 apart, 2 survivors here, 2 survivors at the end. it'll work. You'll feel better. Okay, next one. It's spicy, but I told them this would be on the test, so they should have been ready. Use the integral test to determine whether the series converges. Be sure to check that the necessary conditions are satisfied before performing the test. This is important. So when we do the integral test, we want to look at the integral from 1 to infinity. You just match the limits on the sum. And then you change this to a function, 1 over x squared plus x cubed dx. And before we can perform the integral test, we have to check that f of x, which is 1 over x squared plus x cubed, satisfies 3 conditions. The first are that f is positive on 1 to infinity. Is it? Just do like a quick check. Yeah, we're good. Second thing I want to check, is f continuous on 1 to infinity? Well, what's the domain of f? If I factor the denominator, I take out an x squared, I'm left with x plus 1. So the domain, we have restrictions. X can't be 0 or negative 1. Oh, but lucky for us, neither of those are on the interval from 1 to infinity, so we're good to go. The last thing we need to check is that f is decreasing on 1 to infinity. So there's a variety of ways you can do it. Most of my students love taking derivatives to check this, so let's go ahead. If you want to take the derivative, I would rewrite f of x as x squared plus x cubed to the negative first. It's pretty obvious though, like if you just make these terms bigger, right? The whole thing's getting smaller, so it is decreasing. I didn't need them to be so rigorous, but let's do it. So f prime of x would be negative x squared plus x cubed to the negative second times 2x plus 3x squared. So I have negative 2x plus 3x squared over x squared plus x cubed squared. And then remember here, this is special because we're not plugging in any real number for x. We're only plugging in values from 1 to infinity. Those are the only values that x can take on. So from 1 to infinity, this quantity here, 2x plus 3x squared, that's always positive. It wouldn't always be positive if x could be any real number, but because in the integral test and in this sum, I'm only interested in values of x from 1 to infinity, then it is positive. The denominator is always positive no matter what. And then I got this big old negative sign out here. So I can say with great certainty, this is always negative, which means f is decreasing. So we're good. Okay, that's probably the most like rigorous way of showing it. I didn't need something so full blown, but that's great. Okay, so now we can perform the integral test. Wonderful. So let me drag this little guy down. We may proceed. So what do you do first? Well, with an improper integral, you have to rewrite it as a limit. So I'm going to rewrite this as the limit as t approaches infinity. Integral 1 to t, 1 over x squared plus x cubed dx. Now, how would you evaluate this integral? Well, it's a rational function, so we should do some partial fraction decomposition. Oh yes. So remember, we can take an x squared out of the denominator, and then I have 1 plus x left. And this is, x squared is a repeated linear factor, so the decomp will have the form a over x plus b over x squared plus c over 1 plus x. And then we're going to multiply through by the LCD. So x squared 1 plus x. And I have 1 equals ax times 1 plus x plus b times 1 plus x plus cx squared. And then this is going to be 1 equals ax plus ax squared plus b plus bx plus cx squared. So a plus c is 0. Oh, You guys, I got so in the zone, I forgot to explain what I was doing. My apologies. Okay, so we're going to solve for a, b, and c. So let me look at the coefficients of x squared. There's 0x squared and 0x on the left. So 0 has to equal a plus c. What about x to the first? 0 has to equal a plus b. And then what about your constants? Come to me, little constant. 1 equals b. Ooh, okay, great. So 1 is b. Well, if b is 1, then a is -1, and then that means c is 1, right? Beautiful. So we have the following. Limit as t goes to infinity, integral 1 to t. A is -1, so that's -1 over x. B is +1, so plus 1 over x squared. And then c is also 1 over 1 plus x dx. Okay, let's look at all the terms. Yeah, we can integrate. Let's just go for it. We have here limit t goes to infinity, negative natural log absolute value of x for the first term, antiderivative of 1 over x squared. Remember, this is x to the -2nd. So if I add 1 to the exponent, divide by the new exponent, it's -x to the -1st. I'm going to just write that as -1 over x. Are you okay with that? Oh, good. Okay, plus, last term's just going to be natural log absolute value 1 plus x from 1 to t. Now, since we're summing from 1 to t and t goes to positive infinity, I know none of these values are going to be negative, so I don't have to keep writing absolute value. I can switch to parentheses. If that just makes you turn nervous, then just leave the absolute value. It's fine, but I'm going to drop them now, okay? And substitute in the limits of integration. So we've got limit t goes to infinity. I have negative natural log of t minus 1 over t plus natural log 1 plus t. That's the upper limit. Minus lower limit, negative natural log of 1 minus 1 over 1 plus natural log of 2. Boom. Okay. So let's see what we got going on. This is limit t goes to infinity. Now we just did a problem where we had a limit and multiple natural logs, and I can already see I want to combine these guys because this is going to go to positive infinity. This is going to go to negative infinity. Negative infinity plus infinity is an indeterminate form. And how do we fix it? Well, when we have natural logs, we combine them. So natural log 1 plus t over t. Whichever natural log is positive, that argument goes in the numerator. And then this one's negative, so that argument goes in the denominator. So save that. Then I have minus 1 over t. What else is going on here? Oh, ln of 1, that's just 0. And then this minus sign is going to distribute. So then I have plus 1 minus ln of 2. How are we doing? Are you okay? Yes, you're good? Okay. Beautiful. Now let me clean up in here right before we take the limit, but we're almost there. So this is the limit t goes to infinity, natural log 1 over t plus 1 minus 1 over t plus 1 minus ln of 2. And then now, whew, it's going to be so fun. Are you ready? 1 over t goes to 0. So this whole argument is just approaching 1 now. And then that means I have natural log of 1. That's going to 0. Great. 1 over t goes to 0 as t goes to infinity. And then these two are constant, so they don't go anywhere. They're constant. Good for them. So this ends up being 1 minus natural log of 2. We just did the integral test. What do I care about the integral test when I finish? All I care is that this is a finite number. That's it. It could be 5,042,000, and it would still tell me that the integral was convergent, therefore the series is convergent. So the value does not matter, just so long as it's finite, okay? This tells me that the integral from 1 to infinity 1 over x squared plus x cubed dx converges, which tells me then that the sum n equals 1 to infinity 1 over n squared plus n cubed also converges by the integral test. Now, I want to say something. In the problem, I told them they needed to do the integral test. If you were not told to do it, I hope you wouldn't. I say that because the easiest thing would be just to do comparison to p series. You can say this is less than, take your pick, 1 over n squared or 1 over n cubed, which we know converges as p series, p greater than 1. Therefore, by direct comparison, this series must also converge. That's literally all there would be to it if you weren't told which test to use, okay? But I did want to make sure they didn't forget how to integrate. And I warned them, this exact problem, I told them I was going to put it on the test so they could practice and not be caught off guard. But if you're not told which test to use, sometimes that's better because then you can go for the easiest, most straightforward test. Okay? Good. Good. Now, let's move on to where you're going to have to choose what test to use, all right? Determine if the series converges absolutely, if it just plain old converges, aka converges conditionally, or diverges. Now, I have a whole separate video on this topic because you do need to think in a logical, somewhat tactical approach when tackling these problems. Yes, you do. The first thing you want to go for or test is whether or not the series converges absolutely. That's the first thing, okay? So here we go. What I'm going to do is take the absolute value of the terms. So we're going to test for absolute convergence first. It's the strongest kind of convergence. So if it passes, then we're done, which is nice. So absolute value of an, if I take the absolute value of these terms, all that happens is this little negative 1 to the n would become positive 1 to the n, which is just 1. So then it goes bye-bye. Bye-bye. So I'm just going to write 2n to the 4th plus 4 over 3n to the 8th plus 6. What test should we use? Definitely not integral test, okay? Once was enough. Usually when you have something like this that looks, it's rational in nature, you're going to do some sort of limit comparison with a p-series. And when you're doing limit comparison test, you have to pick what bn is that you're going to compare to. And how do you pick bn? You just look at who's the star of the show in the numerator, who's the star of the show in the denominator. Highest power of n. So we've got n to the 4th over n to the 8th. That simplifies to 1 over n to the 4th. I'm going to let that be bn. And then what do I know about the sum of bn? Don't forget this step. This is very important. Here's the watch out eyeballs. 1 over n to the 4th is a p series. P is 4, which is greater than 1, so this converges. Don't forget to write that because that's crucial in order to justify your conclusion when you finish limit comparison test. So now let's go ahead. Let's use limit comparison test. I'm cool with abbreviations. I always tell my students it's not English class, and if it's like an abbreviation that we all know, go for it. So we're going to have 2n to the 4th plus 4 over 3n to the 8th plus 6 over 1 over n to the 4th, which is the limit as n goes to infinity, 2n to the 4th plus 4 over 3n to the 8th plus 6 times n to the 4th over 1. This is gonna, let's keep cleaning up. Limit n goes to infinity. This will distribute. So 2n to the 8th plus 4n to the 4th over 3n to the 8th plus 6. To evaluate this limit, I want to divide by highest power of n from the bottom, always from the bottom. So divide by n to the 8th. This is now limit n goes to infinity. 2 plus 4 over n to the 4th. This is 3 plus 6 over n to the 8th. As n goes to infinity, this term will go to 0, this term will go to 0, and I'm left with 2/3. What do we care about 2/3? Two things: that it's finite and that it's not 0. But I don't care what number it is. It could be 42. Okay, so what does that tell me? This tells me that the sum, n equals 1 to infinity, of 2n to the 4th plus 4 over 3n to the 8th plus 6 behaves the same or does the same thing as the series that I compared it to. That's what limit comparison lets you say. So who did I compare it to? Why, I compared it to this convergent p-series. So when you get a finite non-zero number, it means they're matchy-matchy, they're twins, they're doing the same thing. So this converges also by limit comparison test. And remember, I took the absolute value of the terms of my original series. So now I can say that the original series, the sum n equals 1 to infinity, that had that negative 1 to the n, 2n to the 4th plus 4, over 3n to the 8th plus 6, this converges absolutely. It didn't even need to be alternating, okay? When you're testing for absolute convergence, you will never use AST. Alternating series test can only tell you that something converges conditionally, on the condition that it's alternating. So when you're testing for absolute convergence, you pick a test other than AST. You can pick direct comparison, limit comparison, integral test, maybe it's geometric, you can do ratio test, you can do root test, etc. Okay? I think that's actually all of them. Okay, that's that one. So we didn't have to check for conditional because it passed absolute convergence. That's the strongest kind. We are done. Done. Move on. Part B. We have the sum n equals 1 to infinity, negative 1 to the n over 5n to the 2/3 plus 8. So again, we're going to test for absolute convergence first. So absolute value of an is 1 over 5n to the 2/3 plus 8. Again, I'm going to go for limit comparison test. Who's the star of the show? Highest power of n in the top and bottom. There's no n's in the top. There's n to the 2/3 in the bottom. So that's what Bn is going to be. You're not done here. What do we know about the sum n equals 1 to infinity of 1 over n to the 2/3? Well, this is a p series. What does p equal? Very good, 2/3, which is less than 1. So that means this series diverges. If you fail to write this part, you would lose points because Bn is a convergent sequence, but as a series, it is divergent. So you have to include this as your justification. Okay, don't forget. P series always start at 1. All right, so again, now we're going to use limit comparison test. So we're going to look at the limit, n goes to infinity, an over bn. So 1 over 5n to the 2/3 plus 8 over 1 over n to the 2/3. This is going to become the limit as n goes to infinity, n to the 2/3 over 5n to the 2/3 plus 8. Again, divide by highest power of n in the denominator. So divide by n to the 2/3. And then let's see. So we've got the limit. N goes to infinity. 1 over 5 plus 8 over n to the 2/3. And then as n goes to infinity, 8 over n to the 2/3 is going to go to 0. I'm left with 1 over 5. What's important about 1 over 5? Not the magnitude, just the fact that it's finite and can't be 0. I just want to talk briefly. If you did get infinity or 0 for the result, It means limit comparison test is inconclusive, and it means that you chose the wrong BN if you get infinity or 0. It doesn't mean you shouldn't have used limit comparison necessarily. It just means this was a bad choice, okay? So what do I know now? Well, I know that my series does the same thing as whatever I compared it to. They're matchy-matchy. So that means the sum, n equals 1 to infinity, of 1 over 5n to the 2/3 plus 8 also does what? Also diverges this time, okay? Also diverges by limit comparison test. So then I know that my original sum that had that cute little -1 to the n, well, it does not converge absolutely. Does not converge absolutely. Are we done? No. Now I'm going to check, does it at least converge conditionally? That's a weaker type of convergence. How do we test for conditional convergence? Always and forever using AST. So I'm going to check, does it conditionally converge? Always use AST. Could I have gone here first? No, because all you would say if you had done AST, you would have proven that it converged conditionally, but you wouldn't have addressed whether or not it converges absolutely. If you're struggling with this topic, you're not alone. Really do check out the video that I have on absolute versus conditional convergence, and I make a whole flow chart and I have this cool analogy. But we just don't have time. Otherwise, this is going to be a 5-hour video. You know what I mean? Okay, so for AST, I have to look at what BN is. And if you remember, BN is your original terms AN just without the alternating part. It's the same as absolute value of AN. So it's 1 over 5n to the 2/3 plus 8. And there's two things I need to check. First, that BN is decreasing. So I'm going to look at BN plus 1. That's 1 over 5 times n plus 1 to the 2/3 plus 8. I can say with great certainty that's less than 1 over 5n to the 2/3 plus 8, which is BN, right? This is a bigger denominator. Obviously, this whole thing's smaller. So BN is indeed decreasing. We're good there. And then the second condition I need to check is what is the limit as n goes to infinity of BN. So that's 1 over 5n to the 2/3 plus 8. Well, this denominator is going to infinity, so the whole thing's going to approach 0. That's what I need. So then that tells me that the sum, n equals 1 to infinity, -1 to the n, over 5n to the 2/3 plus 8, it converges by the alternating series test. And therefore, I can say that the original sum, n equals 1 to infinity, -1 to the n, 5n to the 2/3 plus 8 converges conditionally. Okay, that's a perfect answer. Now, if you just took the test and you stopped here and you didn't write this, I'm not going to take points off, okay? It's all right. But check. My professors at university were like real sticklers. So I did have to be super thorough and precise and add that last statement, okay? I mean, deep down, you should want to. I mean, don't you feel like now we've answered the question fully, right? But if you don't feel that kind of like neurotic urge for perfection, I can appreciate that as well. Okay, last one. Same question. Is it absolute, conditional convergence, or divergence? So here we have the sum, n equals 1 to infinity, -1 to the n, times n factorial squared, times 8 to the n over 2n plus 1 factorial. Now I'm going to tell you this. Majority of the time when you see a factorial sign, you need to use, that's right, the ratio test, okay? So that's what we're going to go for. And also, just so you know, the ratio test is kind of like an all or nothing test when it comes to the question of absolute convergence. So if we get that it converges absolutely. If we get that it diverges, then it diverges. we don't say diverges absolutely, but there's no need to do AST and check for conditional convergence. It's just going to be one of two outcomes, which is pretty cool. So let's go ahead and use ratio test. I'm going to look at the limit as n goes to infinity of the absolute value of an plus 1 over an. So this is going to be the limit as n goes to infinity, absolute value, negative 1 to the n plus 1, n plus 1 factorial squared, 8 to the n plus 1 over, be careful here, 2 to the n plus 1 factorial. Times, I'm going to already multiply by the reciprocal. Are you okay with that? Good. So we'll have 2n plus 1 factorial, and then down here, negative 1 to the n factorial squared, and 8 to the n. Okay? Great. Now, these just go away because I'm taking the absolute value, so they're gone. And then nothing else is going to be negative now, so I don't really need to write the absolute value bars. N plus 1 factorial squared, I think the easiest thing is let's write it out twice. So we know that that means it's n plus 1 factorial, n plus 1 factorial. And I'm going to try to get these guys to cancel with the n factorials down here. So I'm going to break them down. N plus 1 factorial is n plus 1 times n factorial, and I've got another one. And then this 8 to the n plus 1, I'm going to write it as 8 to the n times 8 to the first. Okay? And then what else? Then I still have this 2n plus 1 factorial up here. And then watch out, this is where some people make mistakes. This is 2n plus 2 plus 1 factorial, which is 2n plus 3 factorial. So 2n plus 3 factorial, I'm going to break down into 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, and stop there because see how I have the 2n plus 1 factorial on the other side. So I'm going to stop here, that way I can cancel in just a hot second. And then what's still left? This poor little 8 to the n, huh? I forgot about him. Okay. Oh, and n factorial squared. Oops. N factorial, n factorial. Is that everybody? Let me check. So this is gone. This guy is right here. This is here. Great. Okay. This, I broke it down. This is gone. Here this is. Here's the 8 to the n. Okay, perfect. Cancel party time. So 2n plus 1 factorial is gone. Who else? 8 to the n. You're out of here. N factorial, 2 of them, out of here. So who survived? We've got limit. N goes to infinity. 8 survived. N plus 1 and n plus 1. So I have 8 times n plus 1 times n plus 1 over, watch this. This is pretty cool. I have 2n plus 3 and 2n plus 2. 2n plus 3. 2n plus 2 is 2 times n plus 1, isn't it? Yes, more canceling fun. The party didn't end. And then we can simplify now. Also 8 and 2. Why not cancel that? Boom, boom. That's a 4. Okay, so now I've got the limit. N goes to infinity. 4n plus 4. I'm just distributing. And then over just 2n plus 3. Divide top and bottom by n. And then we're going to have now the limit as n goes to infinity. In the numerator, this is 4 plus 4 over n. In the denominator, 2 plus 3 over n. This goes to 0. This goes to 0. I'm left with 4 over 2, which is 2. What test did I just use? Yep, ratio test. What do I care when I do the ratio test? I compare the limit to 1. 2 is greater than 1. So what does that tell me? The series diverges. Very good. By the ratio test. So I'm going to rewrite it. N factorial squared, 8 to the n, over 2n plus 1 factorial diverges by ratio test. All right, excellent. How are we doing? Good, good, good. Moving on now to the last third of things. Find the interval of convergence of the series. So here we have a power series, sum n equals 1 to infinity, negative 1 to the n, 4 to the n, over rad n times x to the n. So when you're finding the interval of convergence, you need to do the ratio test. Once in a while you can do the root test, but it's not as common. Once in a while you can, but in this case, no, it wouldn't be nice. We're doing ratio test. I can tell the people that's what we're doing. So ratio test time. We're gonna look at the limit as n goes to infinity. Absolute value, an plus 1, so that would be negative 1 to the n plus 1, 4 to the n plus 1, x to the n plus 1, over rad n plus 1, divided by an, so I'm already going to multiply by the reciprocal, rad n over negative 1 to the n, 4 to the n, x to the n. Okay, so the negative 1 to the n's, those are gone because I'm taking the absolute value, they're going to become positive. Let's see what we can break down. I can't drop the absolute value the way I did in the last one because I have x, and x could be any real number. So we must keep it. Okay, limit n goes to infinity. Absolute value. This is going to be 4 to the n times 4 to the first, x to the n times x to the first. I have a rad n over rad n plus 1 times 4 to the n, x to the n. Okay, we get to have another cancel party. Great. 4 to the n is gone. X to the n is gone. Oh, that helps. Now look here, we're taking the limit as n approaches infinity. So 4 and x are constants in this limit, only n is changing. So I can take these guys outside. I recommend you do so, but you do have to keep the absolute value on them. So I'm going to keep absolute value 4x like that. And then I have limit n goes to infinity. I don't need absolute value anymore for the n's because n's going to infinity, it's not going to be negative. And I can just write this as one big happy square root family, square root of n over n plus 1. Okay. Again, to evaluate this limit, divide by highest power of n in the denominator. It's n to the 1/2, but I'm just going to divide by n under the radical. So I'm really dividing by rad n, but I'm putting it under the radical already. So absolute value 4x, limit n goes to infinity. We're going to have square root of 1 over 1 plus 1 over n. And then 1 over n is going to go to 0 as n approaches infinity. So this whole limit is square root of 1 over 1, which is just 1. So now I'm left with absolute value of 4x. And I require that to be less than 1 in order for the series to converge by the ratio test. Now, I want to get x isolated as much as possible. So if I divide both sides by 4, and you can take that constant out of the absolute value, that's not a problem. I get that absolute value of x is less than 1/4. So my radius of convergence is 1/4. So radius of convergence is 1/4. And if I rewrite this absolute value inequality, x is less than 1/4 and greater than negative 1/4, yes? And the problem asked for the full interval of convergence. So I need to test the endpoints and see whether or not they belong to the interval, whether I can include negative 1/4 or positive 1/4. So let's test those separately. But I have the radius at least. Okay, let's do the negative 1 first. So x equals negative 1/4. What do? You come back to the OG series and you're going to substitute in negative 1/4 for x. So I'll do that down here. So we've got the sum, n equals 1 to infinity, negative 1 to the n, 4 to the n, negative 1/4 to the n over rad n. let's clean up this numerator because everything's being raised to the n, so it need not be so messy. I could rewrite that as -1 times 4 times -1/4 to the n. And this is over rad n. -1 times 4 times -1/4, that's just +1 to the n over rad n. I mean, you don't even need to write 1 to the n. It's just 1. So really, this series, if we clean it up, it's the sum n equals 1 to infinity 1 over rad n. Now, we don't even need to do a test. I can just say, hey, this is a p series, guys. Rad n, that means the exponent is 1/2. So p is 1/2, which is less than 1, which means this series diverges, which tells me x equaling -1/4 is not part of the interval of convergence. Okay. What about +1/4? What about that one? Let's see. So then if I substitute in 1/4 for x into the original, I'd have -1 to the n, 4 to the n, 1/4 to the n over rad n. How does this clean up? -1 times 4 times 1/4, that's -1, right? So this is the sum n equals 1 to infinity -1 to the n over rad n. So this time I have to keep that term in the numerator. It's an alternating series, so let's use the alternating series test. How appropriate. Bn is just 1 over rad n. So I need to check two things. Is Bn decreasing? So Bn plus 1 is 1 over rad n plus 1. Yep, that's for sure less than 1 over rad n. So it's decreasing. And the second thing I'm going to check is what's the limit as n goes to infinity of Bn? Yes, it's 0. So that means the sum, n equals 1 to infinity of -1 to the n over rad n converges by AST. And then that tells me, what did I substitute for x? 1/4. That does belong to the interval of convergence. Ooh, so cool. So then you have a close-in interval. I don't know if that's a legitimate term, but we would say that all the time in grad school. So it's half open, half closed. I'm not including -1/4. I am including +1/4. Boom, boom. Okay, very good. Moving on. Next one. That was quite a bit of work. So the next one I gave them was going to be more relaxing. Believe it or not. We have the sum n equals 1 to infinity x minus 5 to the n over 5n factorial. Again, we're finding the interval of convergence. So do ratio test most of the time, especially since I see factorials. It's like, oh, use the ratio test, please, please. So we're going to look at the limit. N goes to infinity, absolute value, x minus 5 to the n plus 1 over 5 times n plus 1 factorial. Make sure you put those parentheses, okay? Divided by an, so I'm just going to multiply by the reciprocal, 5n factorial over x minus 5 to the n. Okay. Now let's start breaking everybody up. We have limit, n goes to infinity, absolute value. I'm going to write this as x minus 5 to the n, x minus 5 to the first. Be careful, be careful. This is 5n plus 5 factorial. I'm going to break that down until I hit 5n factorial. So it's going to be 5n plus 5 times 5n plus 4 times 5n plus 3 times 5n plus 2 times 5n plus 1 times 5n factorial. Finally made it. And then you have 5n factorial up here over x minus 5 to the n. All right, who cancels? X minus 5 to the n and 5n factorial. And that's it. So in the limit, This is where it's a nice time. N's going to infinity. I can take this x minus 5 out, but you do have to keep absolute value, right? Because x could be any real number. So keep absolute value x minus 5. And then we have limit. N goes to infinity. There's nothing left anymore up here. So I just have a 1 over all this mess. 5n plus 5, 5n plus 4, 5n plus 3, 5. Some of them put dot, dot, dot until 5n plus 1, which was fine with me, okay? Now, here's the fun part. So as n goes to infinity, this whole denominator is going to infinity. And I just have a constant in the top. So this is all going to 0. Thank goodness. Which means I'm just left with absolute value of x minus 5 times 0, which is just going to be 0. And that's always less than 1. It doesn't matter what x is. This limit will always come out to be 0, which is less than 1. So according to the ratio test, this series will converge for any value of x, which tells me the radius is infinite in size. And if you have to give the interval of convergence, which I asked for, then it would be from negative infinity to infinity, like that. So no testing endpoints, whew, thank goodness, because it was infinite. So everybody's good to go. How satisfying, huh? Okay, Taylor and Maclaurin series, but before then, one more thing with power series. So find a power series representation for the function and determine the radius of convergence. If you haven't watched my power series made easy video, please do. It will change your life. I'm not being dramatic. Read some of the comments on that video. They warm my heart. Anyways, so there's only 3 cases when you're trying to find a power series representation for a function. And I'm looking, this denominator is squared. So I'm going to start off with power series for 1 over 1 minus 9x and then differentiate until I can get the right exponent in the bottom. So we're going to say, consider 1 over 1 minus 9x. I can write a power series for that. Yes, I can. That's the sum, n equals 0 to infinity, 9x to the n. Since they're asking us to also find the radius of convergence, let's just do it right now while things haven't gotten messy. Absolute value of 9x needs to be less than 1, which means absolute value of x is less than 1/9. So my radius of convergence is 1/9. Boom. This is all based off of geometric series, okay? So that's where that comes from. Let me simplify. This is the sum. N equals 0 to infinity, 9 to the n, x to the n. Good? Okay, now I'm looking. My function has 1 minus 9x squared in the bottom. So how am I going to make that happen? As I mentioned in that other video, never square an infinite series. It's never the answer to your problems, okay? Maybe down the road in some very advanced math class, you'll need to do it, but not here, I promise. How do you get the degree higher? You're going to differentiate. You're going to differentiate. So let me take the derivative of 1 over 1 minus 9x, which I'm going to rewrite it as 1 minus 9x to the negative first. And I'm also going to differentiate the corresponding power series with respect to x. Okay, here we go. So the derivative of 1 minus 9x to the negative first would be negative 1 minus 9x to the negative second times, don't forget chain rule, derivative of the inside is negative 9. Now let's differentiate the power series on the right. Remember, when you differentiate an infinite series, you have to bump up that index by 1 because you always lose that first term. It's just a constant. So the series will always start 1 term higher. So it's going to be at n equals 1 to infinity. And then here, please be careful. Remind yourself, I'm differentiating with respect to x. So if it doesn't have an x, it's a constant. Leave it alone. That's just 9 to the n. Derivative of x to the n would be n times x to the n minus 1. Are we good? We're fabulous, Professor V. Oh, good. Okay. Now let's see. What am I left with on this left-hand side? The negatives cancel. I have 9 over 1 minus 9x quantity squared equals the sum, n equals 1 to infinity, 9 to the n times x to the n minus 1. Is that f of x on the left-hand side? Not quite. Not quite. Here's what I have a power series for. Go us. F of x has a 1 in the top instead of a 9. Oh, we got this. We got this. I'm going to multiply by 1/9. I'm going to multiply by 1/9. Now, lo and behold, these cancel. I have f of x over here. And then I can write this as the sum, n equals 1 to infinity. That's 1/9 when I bring it inside. This is 9 to the negative first, right? So I'm going to have 9 to the n minus 1 times n times x to the n minus 1. And then whenever possible, you want to try to have your power series finish with like x to the n at the end. Sometimes we don't, if it makes the rest of the terms look really ugly, but in this case, let's do it. So I want this to be x to the n. I want this to go up by 1. So I'm going to have to start my sum 1 lower, shift the index down by 1. So f of x is going to be the sum n equals 0 to infinity. And then now I'm going to have, everybody goes up by 1. 9 to the n times n plus 1 times x to the n. And then the radius of convergence, we found it in the beginning. And we're so thankful there's a theorem that told us it's preserved through differentiation and integration. So it didn't change. When we did all this business, it's still 1/9. That's it. Okay. Next one, again, find a power series representation for the following function. F of x equals natural log of 5 minus x. So in this case, if you've watched the video, there's only 3 cases. If you've got an ln, you're going to take the derivative first, find a power series, and then we're going to integrate it. You could sometimes do it in a different approach, but I think this is the most clear for the majority of students doing it this way. My brain likes it better this way. So first I'm going to say, okay, what's f prime of x? Derivative of natural log 5 minus x is going to be 1 over 5 minus x times negative 1, right? Because the chain rule. And I want to try to make this resemble 1 over 1 minus x. So I need this 5 to be a 1. So I'm going to write this as negative 1 over 5 times 1 minus x over 5. You see that? And then I can write this as negative 1/5 times 1 over 1 minus x over 5. Okay, so f prime of x as a power series would be negative 1/5 times the sum, n equals 0 to infinity. You have something to the n. What's the something? X over 5. Good. Let's get the radius of convergence now, okay? Before things get spicy. So this stuff, the something, absolute value of it must be less than 1, which means absolute value of x has to be less than 5. So that's my radius of convergence. Done. 5. Okay, let's clean up this power series here. So f prime of x, I'm going to have negative sum n equals 0 to infinity x to the n over 5 to the n plus 1. Woo, why plus 1? Because I put this 5 to the first inside as well. Okay, good. Look at us. We've got a power series for f prime. Is that what they wanted? No, they did not. They want a power series for f. So how do we get there? Well, I'm going to take the antiderivative of both sides. I want to undo what I just did. So f of x is going to be antiderivative f prime of x dx, which is antiderivative of negative sum n equals 0 to infinity x to the n over 5n plus 1 dx. Okay, don't get freaked out. I know these look kind of intimidating, but you just go, everybody is a constant except for x. So when you take an antiderivative, you add 1 to the exponent and divide by the new exponent. We don't shift any indices. They don't change. Nope, nope, nope. So negative sum n equals 0 to infinity x to the n plus 1, and then I have to divide by that new exponent, leave that 5n plus 1, and then this is an antiderivative, an indefinite integral, put plus c. Okay, we have to solve for c. How do you do it? Well, you look at where your power series is centered at 0. If this was like x minus something, then it would be centered somewhere else, but this is just at 0. So I'm gonna let x equal 0. Then I have f of 0 equals negative sum of a bunch of zeros plus c. And I'm gonna set this equal to whatever f of 0 is. So come back here, come back. What's f of 0? ln of 5 minus 0, so ln of 5. So this all equals natural log of 5. Well, the sum of a bunch of zeros is just 0. So then I can see, all right, c is ln of 5. And then we're pretty much done. Just remember, you don't want to leave this to the n plus 1 if possible. And then, oh my God, everybody's to the n plus 1. It's just begging us to start at 1 instead, right? So I can write f of x as negative sum n equals 1 to infinity x to the n over n times 5 to the n plus ln of 5. And you know I'm not going to leave it like that because we got to put the positive term in the front. Otherwise, it just looks ugly. ln of 5 minus the sum n equals 1 to infinity x to the n over n times 5 to the n. Should we remind them what the radius of convergence is? That would be so nice of us. So let's do it. Okay. Yay. How was that? Enjoyable? Good. Okay, just 2 more. The worst is over. So find the Taylor series generated by f at x equals a. So f of x is e to the 8x, and a is equal to 3. So let's start off making a little table. N, we need the nth derivative at x, and then the nth derivative at 3 in this case, because a is 3. Usually I tell my students, unless terms start like canceling out, going from 0 to 3 is typically enough, okay? So the 0th derivative just means the original function, that's e to the 8x. First derivative of e to the 8x would be 8e to the 8x. Take another derivative, 8 squared e to the 8x, and another 8 cubed e to the 8x. I tell my students, don't simplify so much, because remember, we're looking for a pattern. And so the less you simplify, the easier it is to spot the pattern. Do you know what I mean? Okay. So anyways, from here, and if you do need a review of, definition for Taylor series and whatnot, then go watch the videos. I'm just, I'm going for it. Now we're going to substitute in 3 for x. So this is e to the 24th, 8e to the 24th, 8 squared e to the 24th, so on and so forth. And remember, when you're writing a Taylor series, the terms have 3 components, okay? One component is all the terms from this column here. So that's the first part. Then you always have x minus a to the n, so x minus 3 to the 0 over n factorial. So this is for my n equals 0 term. Okay, let me scoot this over so I can fit all of them. Then let's move on to the next one. So for n equals 1, I have 8e to the 24th, x minus 3 to the 1st over 1 factorial. This is for n equals 1. Plus 8 squared e to the 24th, x minus 3 squared over 2 factorial. This is n equals 2. Plus 8 cubed e to the 24th, x minus 3 cubed over 3 factorial. This is for n equals 3, and it keeps going. So I want you to see there's 3 components to each term. So I'm highlighting in green what came from the column. Then the next part is we have x minus a to the n, And then we have n factorial. And we have to come up with a rule for how to write this in sigma notation, okay? It's not going to be that bad. Keep in mind there's three things. We're going to start n equals 0 to infinity. Let's come up with a pattern for the green terms, okay? I don't see an 8 here. Here's 8 to the first, 8 squared, 8 cubed. The exponent on 8 matches what n is. Do you see that? Because technically there's 8 to the 0 here. Oh, okay. So we have 8 to the n. E to the 24th is there on every single term and it's not changing. So just e to the 24th, add him in. Okay, green part done. Blue part, we have x minus 3. Notice, again, the exponent matches whatever n is, right? Matchy, matchy. So that's x minus 3 to the n. And then in the bottom, n factorial. Now, sometimes it's more difficult than this. Sometimes it alternates or stuff cancels and whatnot. But this one, you know, maybe I took pity on their poor souls. They already had some difficult stuff on the test. Good? Okay, that's it. If you need more practice, I do have extra videos where I do much more difficult Taylor series problems. But this is a good, you know, moderate level, I would say. And then last one, I just wanted everyone to walk out of there happy, okay? Find the Maclaurin series for the given function using a known Maclaurin series, not by the definition. So f of x is x times cosine of x squared over 2. So you should have memorized your known Maclaurin series. Cosine of x is the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial, and the radius of convergence is infinite. So all you need to do is replace x with whatever the argument is here, in this case x squared over 2, okay? So that means cosine of x squared over 2 would be the sum, n equals 0 to infinity, negative 1 to the n, x squared over 2 to the 2n over 2n factorial. Okay, so I literally just came through and substituted in x squared over 2 where x was. And then one more thing I need to do so that I end up with f of x, I need to multiply by x outside. So let me do that also. I'm going to bring it in the sum anyways, but I just want it to match up. Okay, so this is x times the sum, n equals 0 to infinity, negative 1 to the n. This 2n distributes, so then I'm going to have x to the 4n over 2 to the 2n over 2n factorial. Then we're going to bring this x inside, combine it with x to the 4n, and then this guy needs to just come down here, okay, and not make such a mess for us. So then I can say f of x is the sum, n equals 0 to infinity, negative 1 to the n, x to the 4n plus 1. Oh, that didn't straighten up. Oh, heavens. Over 2 to the 2n times 2n factorial. And that's it. That's all they needed to do. So hopefully everybody got 5 out of 5 on that one. I haven't finished grading yet. Okay. Now, I did give them a couple extra credit questions, but this video is certainly long enough. So let me show them to you. You can try them. And then if you want me to record just a little short video solving the extra credit, then let me know in the comments down below and I can do that. So first extra credit, and I always do all or nothing on extra credit. There's no partial credit. Find the sum of the series. Okay. And then the next extra credit, look at me just throwing out points for the people. Find the power series representation of the function. We have natural log 1 plus x to the 4th over 1 minus x to the 4th. Most of these test questions come from the practice exams that I give my students. I also pull some from the textbook, but the practice exams that I give my classes are on my Patreon. So if you want access to some exclusive stuff, extra worksheets and things, you can go sign up. The link's in my description box. I don't really like upload a ton of videos there just yet, just because I'm so busy. So the differential equations, linear algebra videos are also there. They're also available for just if you join as a member to this channel. but like worksheets and stuff, that's all on the Patreon, okay? So I hope you enjoyed the video. Give it a thumbs up. If you made it to the end, let me know. And I also have, like I said, full-length video lectures on all the topics. So I'm just going to link everything in the description that you might need. Also, follow me on Instagram, TikTok, and Twitter, please. I'm trying to get my TikTok to hit 10K sooner than later before it gets banned or something. Oh no, what are we going to do? I love that app so much. I'm debating making Math Police merch. So if you have ideas, let me know. I need some sort of like graphic design. I'll probably hire somebody, who knows. But that's it. I love you all, and I will be back sooner than later. Subscribe if you haven't already. I don't know if I said that. Give me thumbs up. Leave me comments. All right. Mwah, mwah, mwah. Bye, guys.